Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, this is lesson 24, the last lesson in the module, and it is titled Modeling with Quadratic Functions. So the first classwork opening exercise says, draw as many quadratic graphs as possible through the following 2 points on the graph. Okay, so for starters, I am going to assume that this is my vertex here and it's opening up. So if this is the vertex, okay, I'm going to draw an axis of symmetry just to give you an idea. And it would be right here. Let's make that a color I can see. Okay, so there's our axis of symmetry. I'm sorry, that would, well, let's do this one first then. That's fine. Let's assume this point is our vertex and it's opening down. And for that matter, I have to be the same distance because it's symmetric, so I go over 2, and there would be a point here. So therefore my parabola would look like this. Okay, so there's one parabola. Another one would be is if I were to assume, let's use this one, assume that this is my axis of symmetry. What in the world? Okay, let's do this, do this, do this, do this, and make it red, and go through this. Make it a little thicker so we can see it. Okay, that's pretty good right there. So if this was our axis of symmetry, and this was our vertex, then this point has to be the same distance as this point over here, and then this parabola would come down like so, and then go back up like that. So there's two. Okay? So that's assuming that this is the vertex of a parabola opening upward, or we could have assumed this point was a vertex of this parabola opening downward, or we could assume a number of other situations where maybe there was a point, so this would be one of the points on the left side, and this would also be one of the points on the left side, and the vertex could have been somewhere like right here. And if that were the case, then my axis of symmetry would be, let's make this one yellow. My axis of symmetry would be here. I keep forgetting to choose a line segment. All right, and go like that, and yellow. And if this were the axis of symmetry right there, then I would have to choose points that were equidistant from, let's use purple this time. So I'd have to go from this given point here over 1, 2, 3, 4, 1, 2, 3, 4, and put a point here. And this was a given point over 1, 2, over 1, 2, and put a dot there. With this being the vertex going through the two given points, again, it could be right here. Okay? And same goes for one opening up. I could assume that maybe the vertex was, maybe here. And then if I drew my axis of symmetry, I better do this right this time. My axis of symmetry, let's use orange this time. My axis of symmetry is right here. So if that were the case, then I would have to choose points. Let's use orange. I'd have to choose points equidistant from this vertex. So this was our given point. 1, 2, 3, 4, 1, 2, 3, 4 would be right here. Okay. And then this point was a given point right here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 would be out here. Okay. And then that would give us, let's see, I want to just do this here and choose this orange, and so this was my vertex right here. So I have this point here, oops, This is dashed, but that's okay. This point here, coming down through that point, over, up, and through this point here. Okay? So my point is, haha, get it? That there are infinitely many parabolas given just 2 points. When we don't know which is the vertex and which is not a vertex. I could keep going forever and ever, picking different points and assuming that that is my vertex and changing the vertical stretch and so on, and reflecting across, making it negative. So there's infinitely many solutions to this with only 2 points. Okay, so page 2 brings us to example 1. And it says, use the point 0, 4, which is what we were given in the last page, 1, 9, and now they threw in negative 3, 1. So I would graph that here. And it says to write the equation of the quadratic function whose graph contains those 3 points. So now if I try to do what I did on the last page, it's not going to work because there aren't multiple possibilities here. For instance, if I thought this was my vertex and this comes down here, well, it's got to go over to here. And then if this is my axis of symmetry, this is negative 3 and this is 1, that's a distance of 4. So 1, 2, 3, 4 would be over here. And if I graph that, it comes down like this and goes out like this. Well, that's obviously not a parabola. So I can't do that. So that's one situation. So let me undo all that. So now we're back to here. So that can't be a maximum, and no other point can be. A parabola comes down, it doesn't turn and go the other way. So I can't have something that's curving like this and then curving like this. It's impossible. That is not a parabola. All right. So the only situation I have here is this cannot be the vertex either, because this point would be here and this point would be here, and I can't come down like so and then go like that. That's a cubic right there. So I can't change direction, so that doesn't work. So this is looking like it is a parabola opening upward, and this might be the vertex. But if we make a table of values, so if I do x, y, and make a table, and I have the point negative 3, 1, and I have the point 0, 4, and I have the point 1, 9, which is what we were given, okay, and I find the difference between x, or the y's here, the difference here we had to add 3, and here we had to add 5. So if I did this in a table, here, let me get rid of these things here. Let me do it in a table differently. So if I make another column, and if this was y1 and this is y2, then this would be y2 minus y1. So if this is my y2 and this is my y1, it would be 4 minus 1, which is 3. If this were my y2 and this were my y1, 9 minus 4 is 5. And then I could call this one my second difference. Second difference. Well, the difference between 5 and 3 is 2. So then I can choose other values that would make this true. Okay, so now if I want a second difference, I can work backwards. So if I just put a 2 here, because if this is a quadratic, your second difference has to be the same. So if I had a second difference of 2, then this number here would have to be 7, because 7 from 5 to 7 is a difference of 2. 7 minus 5 is 2. Well, if my difference from 9 to a number is 7, well, 9 plus 7 is 16. So I have a value of y being 16. Where would my x land? So if it's 1, 9, would it be 2, 16? This is going from 0 to 1, and this is going from 1 to 2. but this went from 0 to negative 3. So this could be a possibility. And then if I do another difference of 2, then that would be 9. And 25 minus 9 is 16. And would that be 3? So then 325 maybe. So you see what's going on here. I'm trying to figure out what these values are. So then when I do a common difference, let's drag this down here. And I'm going to move all my values down a little bit and go the other direction on my grid. You can just put a negative 1 here, negative 2 here, but I want to keep them in order. So you don't have to erase if you've already done this. I just want to make it clear as to what's happening here. Okay, so as you can see, I went from 0 to negative 1. I squeezed in negative 1 and negative 2 here, so these are in order of 3, 2, 1, 0, negative 1, negative 2, negative 3. So if this is a common difference of 2 here, this is 3. 3 minus 2 is 1. If this is a common difference of 2 here, 1 minus 2 is negative 1. And if this is a common difference of 2, negative 1 minus 2 is negative 3. Okay? And so on, and so on, and so on. So now I need to know if this is a difference of 3 from 4. 4 minus 3 is 1. 1 minus 1 is 0. And 0 minus a negative 1 is positive 1. So this seems to be working. So if I go negative to 0, that would be here. Negative 1, 1 would be here. And now we can see if we continue, I'm going to change colors now. If I continue this way, if I go to negative 4 and there's a common difference of 2, then negative 3 minus 2 is negative 5. And 1 minus a negative 3 is 1 plus 3, which is 4. So it would be the point negative 4, 4. And as you can see, if this were my vertex now, let me draw a vertex. Let's do it in red. If this is my vertex right here, or my axis of symmetry, I mean, and this is the vertex, you do see now that I go over 2, and I'm on that point. Go over 1, 2, I'm over 1, 2, I'm on that point. Over 1, 2, 3, 1, 2, 3, I'd be over here. So if I went to negative 5, I should be at 9. Okay, so now I can see that this is a parabola. Whoops, let me switch back to just a line. So this is a parabola coming down. My minimum is right there, or my vertex, and then it turns and goes back up. So, given 3 points, there's only one possible parabola, and there it is. And then it says use the points to write the equation. Now we need to write an equation for this. Well, then we use our given information. The point 0, 4 is the y-intercept right here. So the vertex is the point negative 2, 0. That's the vertex. And the y-intercept is the point 0, 4, or y equals 4. So with those two values, I can construct a function that is the parabola that this fits. So if we have y equals a times x minus h quantity squared plus k, and I know my vertex is the point negative 2, 0, then it's y equals sum a times x minus a negative 2, or x plus 2 quantity squared plus 0 is the vertex form. Okay, but then my y-intercept is 4. Okay, so at this point, we do know the vertex, we know the y-intercept, and if I put it in vertex form, we still have unknowns. We don't know what a is, and we don't know what y is and x. So we could continue by playing around with this, but let's go back to prior lessons in this module, and we will use systems of linear equations or systems of equations to solve this. So in order to do that, we're going to use the points. So if I use the point that we were given, 0, 4, so if I use 0, 4, in the equation, f of x equals ax squared plus bx plus c, the point 0, 4 is my y-intercept. That means x is 0 and my y-intercept is 4. So f of x is y. So I'd say 4 equals a times 0 squared plus b times 0 plus c. So 4 equals 0 plus 0 plus c is just simply c. So we now know c is 4. The y-intercept is 4, the constant at the end of a quadratic. So now let's use the point 1, 9. And if I use the point 1, 9 and I use that f of x equals ax squared plus bx plus c, now my y is 9, or my f of x is 9, my x is 1. And that will give me 9 equals 1 squared is 1, so that would just be 1a, or just a, plus b plus c equals 9. But we could also get rid of this c now because we found out c is 4. So I could put a 4 here. So I can substitute in 4 for all of my c's. Okay? So once that's a 4, then when I move 4 over to the other side, by subtracting 4 from both sides, I will get a plus b equals 5. So now I know the sum of a and b is 5. But they also gave us the point -3, 1. So if I use that point now, in f of x equals ax squared plus bx plus c, and my c is 4, remember, and my y is 1, and my x is -3 this time, then I get this. And then when I simplify, -3 squared is 9a minus 3b plus 4. Move the 4 over to the other side and I get -3 equals 9a minus 3b. So there's my system of equations. So I can have, now I'm going to move down. I'm going to take this equation here and this equation here, and that is a system. So I'm going to have a plus b equals 5 and 9a minus 3b equals -3. Okay, so to solve this, I can multiply this by by 3. And why am I doing that? That will eliminate the b. So if I multiply this by 3, I will get 3a times 3b plus 3b equals 3 times 5, 15. Just bring this back over, 9a minus 3b, no changes to the bottom one, equals -3. And now when I add these two, and I'll put a circle around that plus, I'm adding these two. 3a plus 9a is 12a. 3b plus a -3b cancels. 15 plus a -3 is 12. That divided by 12, and I found a is 1. So if a is 1, I go over to this equation, 5 equals 1 plus b, subtract 1 from both sides, and I get 4 equals b. So now I have my a, I have my b, and I have my c. So my equation is y equals, or f of x equals, let's not use y. So my equation is going to be f of x equals a, which is 1, x squared, I don't need to write the 1, b is 4, so that's plus 4x, and c was 4, plus 4. So my equation is f of x equals x squared plus 4x plus 4. Now let's check it. Let's put this 3 in, and I should get 25. 3 squared is 9, 4 times 3 is 12, 9 plus 12 is 21, plus 4 is 25. It worked. Check 2. 2 squared is 4, plus 4 times 2 is 8. 8 plus 4 is 12, plus 4 is 16, and that is 16. So just checking those two, it worked. If I plug in 0, I'm obviously going to get 0 squared plus 0 plus 4, which is 4. So there's the equation of the parabola going through the 3 given points. Okay, page 3 brings us to exercise 1. Try this, pause the video, see if you can do it. It says to write in standard form the quadratic function defined by these 3 points. See if you can come up with the answer to this and without graphing. So we are given 3 points. Pause the video, do this, and see how it goes. Okay, assuming that you've done that, we have a point 0.05 over 0 up 5. That is our y-intercept. Okay, this is our c. 5 zeros a root or a solution when y is 0. We're on the x-axis. Across the x-axis at 5, 0, and we have the point 3, negative 4. So for starters, if we take the point 0.05 and we use f of x equals ax squared plus bx plus c, and substitute in the givens, y is 5, x is 0, and when I solve this, I get 5 equals c. Okay, there's our constant at the end of our quadratic. So my equation is going to be f of x equals some x squared plus or minus some x, and then at the end it's going to be plus 5. So we've got that component so far. We need our linear component, our sines, and our a. We need a, b, and we're done. Okay, so then we're going to take the next point, 5, 0. Let me change colors. 5, comma 0, using the function f of x equals ax squared plus bx plus c, then we get 0 equals a times 5 squared plus b times 5 plus my c, which is 5. Don't forget that. So 0 equals 25a plus 5b plus 5. Okay, getting a and b by themselves, that would give us negative 5 equals 25a plus 5b. And then finally, we're going to do the point 3, comma, negative 4 with the function f of x equals ax squared plus bx plus c. So f of x is negative 4 equals a times 3 squared plus b times 3 plus my c, which is already 5. Move that 5 over here and I get negative 9 equals 3 squared, which is 9a plus b, 3b. We are going to use this equation and this equation, solve the system for a and b, and we're done. Okay, so let me get this other problem out of the way. Okay, so now I'm going to line these up. So I have negative 9 equals 9a plus 3b. And I have negative 5 equals 25a plus 5b. Okay, so what I need to do is manipulate these, one or the other or both, to get an opposite or a same and add or subtract the two. 3 and 5 has a common factor, greatest common factor, or common multiple, I should say, least common multiple of 15. So let's try to get 15. So if I multiply this first one by 5, that will give me negative 45 equals, multiply here, 45a plus, multiply 5 here, 15b. Okay, let me move this equation. Okay, exercise 2 says, Lewis dropped a watermelon from the roof of a tall building. As it was falling, Amanda and Martin were on the ground with a stopwatch. As Amanda called the seconds, Martin recorded the floor the watermelon was passing. They then measured the number of feet per floor and put the collected data into this table. Write a quadratic function to model the following table of data relating the height of the watermelon distance in feet from the ground to the number of seconds that it passed. So we have a table here, height, distance from the ground, for a watermelon that was dropped from a tall building. Time t 0, the height in feet was 300 feet. So this guy was at the top of a 38-story building. After 1 second, it had gotten to the 284th floor. 2 seconds, it was down to the 236th floor. 3 seconds, it was down to the 156th floor. Or, no, I'm sorry, 15th floor. So generally, when a building is built, there's about 10 feet per floor. That's why I'm saying this. So 300 feet would be a 30-story building. 284 feet would be somewhere on the 28th floor. 236 feet would be somewhere on the 23rd floor, and so on. So 3 seconds, 15th floor. 4 seconds, somewhere on the 4th floor. How do we know this data will be represented by a quadratic function? Okay, so if it's quadratic, then we have to have a second difference that is equal. So I will do first differences. So 300 minus 284, that is a difference of 16. Okay, the difference between 284 and 236 is 48. And 156 to 200 is 44. 44 plus 36 is 80. Okay, and then 156 down to 100 is 56, and 100 down to 44 is 56. So 56 and 56 is 128. No, it's 112. 112. The difference between 16 and 48. 32. 48 plus 32 is 80. And 80 plus 32 is 112. So we do get a second difference of 32. So how do we know this data will be represented by a quadratic function? It has the same second difference. And by the way, these were all negative. So that should be negative 16, negative 48. It decreased by that amount. And these are all negative as well. A difference of 32. B says, do we need to use all 5 data points to write the equation? And the answer is no. We only need 3. And it's very helpful to have the y-intercept, because we already know C is 300. And I think that is the next question. Okay, page 4 brings us to part C. I've already brought in the table from the prior page because we're going to use it here. And it says, are there any points that are particularly useful? And does it matter which ones we use? Write a quadratic function that models the data. Well, yes, there are definitely useful points. Y-intercepts are always useful because if I use the point 0, 300 in my equation, f of x equals ax squared plus bx plus c, then this is my y, or f of x, a times 0 squared plus b times 0 plus c will give me 300 equals c. So I've already got my constant for my quadratic. Does it matter which ones we use? Yes and no. If we use smaller numbers, it's easier to work with. 1 and 2 for my a and b would be great, or my x's. And so anyhow, when I use the point 1 comma 284 in my quadratic formula here, f of x is 284, and that equals a times 1 squared, which is 1, a times 1 is a, plus b times 1, which is b, plus 300. So just using 1 makes it really easy to work with. And so then when I subtract 300 from both sides, we get an equation in the form of a plus b equals something. Okay, so when I subtract 300 from both sides, that shouldn't be there, I get negative 16 equals a plus b. So I'm going to use this equation in my system, and then I'm going to come over here and I'm going to use the point 2 comma 236, and that will be 236 equals a times x squared, which is 2 squared, which is 4a, plus b times 2, which is 2b, plus 300, which is our c. Subtract 300 from both sides, and that will give us negative 64 equals 4a plus 2b. So now I'm going to do a system using those 2 point lines, those two linear terms. So it's going to be negative 16 equals a plus b, and negative 64 equals 4a plus 2b. Well, the easiest way to get rid of these is work with the smallest number, and I want to get rid of this 2b, so I need a negative 2. So if I multiply this whole thing by negative 2, that is going to give me negative 2 times negative 16 is positive 32. Negative 2 times a is negative 2a. And negative 2 times b is negative 2b. And then I just bring over my other equation, negative 64 equals 4a plus 2b. And then when I solve this, I get negative 32 equals 2a, and that goes away. Divide by 2, and that gives me a equals negative 16. So now I have an a, I have a c, I just need b. I will use this equation here. Negative 16 equals a, which is negative 16, plus b. Well, if I add 16 to both sides, then I get 0 equals b. So my equation is now going to be, oh, by the way, it's t, so I shouldn't be using f of x, it should be f of t. So it's f of t equals a x squared plus b x, 0x goes away, plus c, which is 300. So my function is f of t equals, let me fix this, and I'll show you why I'm erasing this, 16t squared, not x squared, plus 300. All right, so this is the equation in terms of t. F of t equals negative 16t squared plus 300. Okay. Okay, part D says, how does this equation for the function match up with what you learned about physics in lesson 23? Is there a more efficient way to find the equation? Okay, well, if you look at this equation, negative 16t squared is our gravity pull of the Earth, plus 300 is our initial position, and holding a watermelon and not throwing it, the initial velocity is 0. So this is perfect. This is the equation. So it matches perfectly. This equation shows that the initial position height is 300 feet and the initial velocity is 0. It correctly used negative 16, that's the leading coefficient for gravity. And we would have written the equation directly from the information provided, since we already knew the initial height and velocity. So that could have been a lot easier on us. Part E says, can you use your quadratic function to predict at what time t the watermelon will hit the ground, i.e. f of t equals 0. And the answer is, of course, yes, of course. F of t equals negative 16 t squared plus 300. F of t is 0 equals negative 16 t squared plus 300. Subtract 300 from both sides, and I get negative 300 equals negative 16 t squared. Divide by negative 16. Divide by negative 16. Okay, get my calculator. 300 divided by 16. 18.75. Negative divided by negative is positive, so I didn't use my negatives. Okay, so it is 18.75 equals t squared. Take the square root of both sides. Okay, don't forget your plus or minus here. Bring this up. So t equals the square root of 18.75. So square root, second answer, enter, and it's 4.33 approximately. So I'll put in approximately 4.33. And that would be seconds. So in about 4 1/3 seconds, that watermelon's going to splat on the ground. Okay, page 5 brings us to the end of lesson 24. Review the lesson summary and go to your problem set.